Metallic nanoparticles are essentially small, tightly packed spheres of metal which give off ions when placed in water. Zinc oxide nanoparticles in particular are very common and possibly one of the most widespread of these chemicals. These released ions can be extremely toxic to aquatic organisms and can have devastating impacts on the ecosystems to which they are introduced. Now you may ask, why study these nanoparticles when we know that just unaltered zinc ions are the thing that is toxic? Well, prior research has proven that nanoparticles are more toxic to organisms than just their equivalent amount of zinc ions. It's still up in the air, but many scientists think that nanoparticles have special properties which allow them to grab organisms' proteins and shoot out ions at a faster rate right at the organism. Essentially, they are like the raid wasp killer of the metal world. In addition, nanoparticles are much more widely used than metal ion solutions and can be found in more everyday products than you may think. That superpowered sunscreen that you use which says contains zinc on the front probably has zinc oxide nanoparticles in it. Antifungal sports clothing at the store, most have either copper or silver nanoparticles. Even some medical instruments are sterilized using nanoparticles. So, nanoparticles are used all over and have many different applications. This means that inevitably, they are going to end up in a stream or a lake, especially if we are considering people who put on that zinc nanoparticle sunscreen and go for a swim. This means that the measurement of how fast they dissolve is of utmost importance, as it gives us an idea of how much toxic material we are putting into aquatic habitats. Now, there is a very interesting paper titled Direct In Situ Measurement of Dissolved Zinc in the Presence of Zinc Oxide Nanoparticles Using Anodic Stripping Voltammetry, written by Jiang and Hsu-Kim and published in the Journal of Environmental Science in 2014. At first glance, it seems like a whole lot of jargon and little else. However, if we were to translate this title into understandable English, it would read something like, Measurements of how fast tiny spheres of zinc dissolve into water. This paper seems inaccessible at first, but after our switch from jargon to English, it seems a lot more manageable, and maybe even more interesting to some. Garnering interest in this kind of work is important because it has significant environmental applications which should be widely available to the public. Currently, however, papers such as these are behind not just a journal paywall, but also a vocabulary wall of sorts. The major goal of Jiang and Hsu-Kim's paper is the development of a quick and accurate way to measure how fast zinc oxide nanoparticles dissolve. They spend a fair amount of time going over a technique called anodic stripping voltammetry, or ASV. Essentially, what they did is electrically charge a mercury drop held in a small container with a negative charge, making the positive zinc ions in a sample of water stick to it. They then switched the mercury to a positive charge, thus releasing all of the previously stuck zinc. This releases a very small current, which they measured and equated with the amount of zinc that is in the water. This seems like a very roundabout way of measuring something, but in fact it is by far the quickest and least labor-intensive method we have seen to date. In addition, it can take measurements in quick succession, allowing rates of dissolution to be calculated. Currently, the most common method used to measure ion concentration is called inductively coupled plasma mass spectroscopy, or ICP-MS. This technique, in addition to being extremely expensive, the machine costs almost $500,000, cannot measure data in a way that lets us know how fast the zinc dissolves, only how much has dissolved. In the future, we can expand studies like these by performing experiments in conditions closer to that of the natural environment, such as in more complex experimental conditions or in the presence of actual organisms. If you are wondering what impact you can have in this line of study, you can support proper disposal of industrial nanoparticle waste by voting for representatives in your city or state with an environmentally friendly agenda. But we cannot completely rely on government regulation to mitigate environmental damage. Watching where we throw our waste and being aware of the contents of the products we use every day is becoming increasingly important for those humans who wish to protect our planet and the wildlife we share it with. As consumers, it is part of our responsibility to research how the products we buy are made and balance these products' utility with their potential environmental impacts. In order to educate yourself, however, you need to have material to read in the first place. Researchers such as Jiang and Hsu-Kim and many others need publicity and financial support to continue expanding the field of toxicology with respect to nanomaterials. You can help scientists by supporting the National Science Foundation, the National Institute of Standards and Technology, and any other major contributors to the funding or execution of new and exciting science surrounding nanoparticles.